What we're going to do in this segment, we're going to take a look at how heat transfer relates to a couple of other subjects that you'll encounter in this area of the thermal sciences, and those are thermodynamics and fluid mechanics. So heat transfer obviously is related to both thermodynamics and fluid mechanics, and what we'll begin by doing is taking a look at thermodynamics. So if you've taken a course in thermodynamics, you're fully aware that in thermodynamics, we always talk about heat interaction. We talk about heat interaction, work interaction, and the change in the internal state of matter as it goes through transformations from one state to another. But essentially within thermodynamics, we're always dealing with the conservation of energy, and that's the main law that we use when we look at thermodynamics. And you could have either a closed system or an open system, and depending upon the system that you're using, the conservation of energy or the first law of thermodynamics will look a little different. So let's take a look at a closed system to begin with. So when we're dealing with closed systems in thermodynamics, quite often what we will show is interaction between the system and the surroundings, and interactions can be in the form of heat transfer, Q. And I should point out, and I'll make a comment in a moment, I'm using heat transfer's designation for Q. So if you think this looks a little strange from a thermodynamics course, that's the reason. But what we have is we have heat interaction, we have work interaction, and we have a change in the state. And in this case, we're looking at internal energy of our fixed mass system. And usually when we write out the first law, so if we're writing out the first law for this type of system, it would look something like this. So what we have is we have heat transfer in minus work. In this case, it is going out is equal to the change in internal energy per unit time. Concerning the units, I need to make a little bit of a comment here about the units that we're going to use. And if you recall from thermodynamics, and what we'll do, we'll take a look at the units for heat transfer. So quite often we'll have capital Q. Sometimes you'll see capital Q dot, and that would denote joules per second. And then other times what we do is we divide by the mass flow rate, or m dot, and that gives us a little q that we use in thermodynamics, and that's usually energy per unit mass, so I'll put kilojoules per kilogram. And that is what we've used in thermodynamics. Now, when we're dealing with heat transfer, what we do, we use designation little q, and that denotes joule per second or watt. And so those will be the units that we use in heat transfer. And you notice by comparing these two together, they're different. And so just don't get confused by that. In heat transfer, little q denotes joules per second. And that's why this version of the first law might look a little funny or strange if you've just taken a course in thermodynamics or if you remember thermodynamics. But that would be how heat transfer is involved in a closed system. So what we'd be doing in heat transfer is determining what this value of Q would be. That usually when you're solving problems in thermodynamics, Q is usually assumed or given. And if you recall in thermo, we also had systems where mass could be crossing our boundary, and those are open systems. And so what I'm going to do, I'm going to write out what they sometimes call the fluid kidney. So it's just some system. So there we have our system. We have mass crossing a couple of boundaries. We have an inlet and we have an exit. And given that we have mass crossing the boundaries, we have to be a little careful with the first law of thermodynamics. And we usually have information about the state coming in and the state leaving. And that is usually in the form of things such as the internal energy, little u, PV, which is pressure times the specific volume, and the velocities. So that would be on inlet, and then on exit we would also know that information. Now we put this all together and that goes into the first law of thermodynamics. So writing out the first law of thermodynamics for an open system, we have the following. Okay, so there is our first law of thermodynamics. Sometimes what we'll do is we'll cluster this into the enthalpy. And this is our kinetic energy, and this is our potential energy. And we have mass flow rate coming and multiplying as a pre-multiplier in both the inlet and the outlet. And then we also have our heat transfer and we have our work. So in this course, we're going to be focused on, again, estimating what that heat transfer might be. And that is, again, something that is quite often assumed or just given when we're doing thermodynamic calculations. So that is an open system in thermodynamics and where we see places where heat transfer comes in. And I just want to make a comment about thermodynamics. I'm going to write that out next. So when we're studying thermodynamics, as I mentioned, quite often the heat transfer is given. And so thermodynamics tells us nothing about the mechanisms that the heat exchange is taking place under, nor does it provide methods for computing the rate of heat exchange. Now, sometimes you'll give a problem where you can't actually calculate Q, that might be for a particular system, but you have no method of actually going in and calculating what that heat transfer would be for given scenarios. And so that's what we're going to be doing in this course. We're going to be looking at the mechanisms of heat transfer, and we will be estimating the values of the heat transfer. And with that, you're better equipped to be able to go in and then analyze systems, be it with thermodynamics or fluid mechanics, which we'll get to in a moment. But what we're going to do, let's take a look at a brief example that kind of illustrates this. And what we'll do, we're going to look at the case of throwing an iron ingot that is being quenched in oil. So there we have our problem statement. You look at any thermodynamics book under closed systems, fixed mass, and guaranteed you'll find questions that look like this. So in order to solve this, what we want to do, we want to find what is the change in internal energy for an iron ingot that is quenched in oil and is going from 1,000 degrees C down to 100 degrees C. So if you're doing thermo, what you do is you would go and you would find, well, we have to get the specific heat. And if you recall, du is CV dt. So that is a way to evaluate the change in internal energy. Now we're dealing with a solid, and consequently CV equals Cp. And so we don't really have to worry about that. But we then go in and we evaluate the change in internal energy. And we can plug in the values. Okay, so that's pretty typical of something that you'll see in thermodynamics. You evaluate 405 kilojoules. Everything seems great. You've solved the problem. However, there's some other questions that you may ask. Let's say you want to know, how long is this process going to take? Well, looking at this, you have no idea. You have no way of being able to figure that out. Another thing, let's say we're dealing with ingot of iron quenched in oil. Let's say you're studying material science and you want to understand what the microstructure is like on the inside of this ingot as it's going through this quenching process. So that means that you want to know what is the temperature distribution inside of this iron ingot and how is it going to change with time. Well, with thermodynamics, you cannot figure that out. And so what we need to do, we need heat transfer in order to figure those things out. With heat transfer, be able to figure out the convective heat transfer coefficient on the outside. That would help us figure out how long it's going to take. And we would also use conduction and the heat diffusion equation that we'll be looking at in this course to figure out how the temperature on the inside of this iron ingot is going to change as a function of time. So the questions that we might ask: so you might want to know how long is it going to take, and temperature distribution. Heat transfer gives us these answers, and so that's why you're studying and watching this video, hopefully, and we'll watch more videos, and that way you'll be able to figure out how to solve this using heat transfer. And if you're not interested in that and you just want the thermodynamic approach, go and watch the thermodynamics course. Okay, so that's thermodynamics. Let's take a look next at fluid mechanics. And the place where fluid mechanics comes in to heat transfer is when we have convective heat transfers. So let me scroll back here. This was from the previous lecture segment, and what we did is we had convection here. So we looked at convection, convective heat transfer. We talked about that, and you have a moving fluid coming over some surface. Here I draw it as being a really nice flat plate, but it could be any kind of irregular surface. So that is the place where fluid mechanics comes into heat transfer. So what we'll be doing in this class, we'll be taking a look at convection. In the course, we'll be looking at both natural and forced convection. Natural is where the buoyancy force is what is driving the fluid, and that provides the energy exchange. Forced convection is where you'd have a pump or some sort of fan or blower moving the fluid over the surface. And what happens is we can do analysis up to a point. We can do laminar analysis, but as soon as you start getting complex shapes and if you get turbulence forming in the convective heat transfer over the surface, so let's say you had a turbulent boundary layer here, then all of a sudden it becomes very difficult to be able to predict what the heat transfer rate is, and we usually show that with the convective heat transfer coefficient. I won't get into that yet. I'll do that in a later segment here. But when you get turbulence, then you need to use empirical data. So basically you conduct experiments and you use non-dimensionalization, non-dimensional numbers in order to come up with the estimates for the convective heat transfer that would be for fluid mechanic flows over heated objects or cooled objects. So that is